Officially called observational astrophysics. I was thinking that I should bring some observational aspects of studies of extrasolar planets to the theoretical center like NORDITA, and I'll try to sort of be not so much detailed, but try to be a little bit provocative, trying to explain what would be needed in the nearest future in terms of modeling to interpret the observation. So, the first part, I'm going to talk about observational efforts to detect exosolar planets. I will concentrate on two types of observations which have been more successful, and that is radio velocity searches and transits. Then I will talk a little bit about characterization of extrasolar planets, and the last part of the talk will be models or model requirements. So, current status, we have 293 planets discovered in 244 planetary systems. The largest planetary system known today contains 6 planets, and that is of 25th of May. Planets are coming, popping up like mushrooms, so you never know if there will be 3 or 4 more discovered in a couple of days. I guess the most important thing is up to now, 260 have been discovered with radio velocity searches. There are a couple of unclear cases where transit people claim that they discovered those first, or radio velocity people said. But we've been sitting on these stars for like 3 years, and we already suspected that it was a planet. So sometimes the situation is unclear. In 21 cases, transits have been discovering new planets. And in total, there are 51 transiting systems known. So on several occasions, it was the radio velocities that discovered an extrasolar planet, and then from estimates of the orbital elements, people said, well, there is a high probability that the system would have transits. And then people went and looked for transits, and there it was. And less than 10 in total have been found with microlensing or timing. And timing is a technique which is used in case when people are looking for planets around pulsars. And there are 3 such planets known up to now. So, radial velocity measurements, essentially it's Kepler's law. You have a planet orbiting a central star, and the star wobbles. Sorry, this is the star, this is the planet, this is a planet here, this is the gravity center of the system, and both are planet and star moving around common gravity center. And of course, in practice, the gravity center of the system is actually inside the star. But still there is a residual velocity on the star, and that's what we try to measure. There are 2 leading groups, which and the difference between them is not only geographical, but primarily the technique that they are using. One group, which is U.S., essentially centered in Berkeley, led by Jeff Marcy, but are several independent subgroups and so on. These people are relying on internal calibration of your data, where you mix the calibration signal with the actual signal from the star. So the references are built into your data. The advantage of this technique is that you are not relying on the stability of the telescope, other instruments, spectrograph and other instruments that you are using. The main reference is already in the data, and it's going through the same path as the data from the star. The way the reference signal is built in or is introduced is through absorption cell. So you send the star signal through a cell of gas that absorbs at a different wavelength position. There are different lots of reference lines that you can use. Those lines are very narrow and very stable because you control the conditions, the density, the pressure and the temperature in the sun. Alternative approach is to create an ultra-stable instrument with external, zero-point reference, and that can be, this is of course much more expensive technique, and that requires dedicated instrument and almost dedicated telescope. In fact, that's what European Southern Observatory is running now. The 3.6 meter telescope on La Silla is fully dedicated to this thing, and during the observations, even the building is vacated because they want to shut down air conditioning in the system so that to avoid extra vibrations. This has interesting advantages. Both methods have advantages and disadvantages, and people realize the problems and the systematic effects, and they're working hard. And the current goal for both teams, or both sides of the Atlantic, is to reach 1 centimeter per second precision. So in fact, this is log law that you find when you enter Berkeley astronomy department on the wall. And also, not surprisingly, Geneva guys are also struggling to reach 1 centimeter per second. If you think about it, it's quite spectacular. It's 11th order of magnitude relative precision. It's really, it's shockingly amazing. I'm moving faster now than 1 centimeter per second. Okay, so let me dive a little bit into more details in radial velocities with iodine cell, or with absorption cell. In this case, the iodine cell is used. Iodine is heated to something like 100 degrees Celsius and then evaporates. That produces lots of narrow lines, and here is a fragment of iodine spectrum. Never mind the spectral region, it's around 6,000 angstrom here. It's rather short. We're looking at 40 angstrom in this range. So what you're actually observing is the black line here. The black line is the stellar spectrum, which is shown in blue here, which is sent through the iodine cell, and then the absorption lines of iodine are superimposed on the spectrum of the star. So the equation that you have to solve is the following. Here is your observation. So observation is the black line here. Okay. This is the stellar spectrum, which is shifted by the radial velocity. That's the blue line. This is iodine spectrum that you know because you do laboratory measurements of iodine spectrum, very precise. Usually you actually know it to much higher spectral resolution as well. And this is a point spread function where the finite resolution of the instrument that you're using to observe this thing. This is something you don't know. This is something you have to recover. So essentially what you do, you're trying to take the template, your best knowledge of the blue spectrum, multiplied by iodine spectrum that you know very well, and then convolve it with unknown point spread function that you have some estimates of. And then you iterate until the left-hand side matches the actual black line. It's a typical inverse problem. It's Fredholm equation in that case, so you can think of different ways of solving this problem. But there is a fundamental difficulty in this whole thing, and that's what is the next step for Berkeley guys to reach 1 centimeter per second. And that is the resolution with which the stellar spectrum, the template, the blue line is known, is usually the same resolution with which you're taking the black spectrum. Now, if you want to do the convolution, you have to really oversample. You have to have high spectral resolution before you can actually do multiplication and then the convolution, because otherwise you're more or less doomed. And that's a tricky part. That's not a trivial part, because how do you improve the resolution of the instrument which is meant to reach certain resolution? That's what they're working with. So that's a difficult part, and they're looking at different ways of improving the resolution by dithering, by oversampling, and so on. So that's their current practical work to reach 1 centimeter per second. By the way, 1 centimeter per second is not just a good number. The effect of the Earth on the Sun, on the Earth orbit, in terms of radial velocities, is few tens of centimeters per second. So you need precision of 1 centimeter per second to detect Earth-like planets on Earth-like orbits. Now, the alternative, the European sort of approach, is through building dedicated spectrographs, which are incredibly stable. Michel Mayor was giving a talk in Royal Academy a few weeks ago, and he referred to this particular incarnation of the idea, which is called HARPS, as Lamborghini of spectrographs. I think it is, also considered the price tag. But what they basically do, they put this thing in completely isolated environment where they control the temperature and the pressure to the precision of about 10 to the minus 4 inside. So the whole spectrograph works in vacuum, and the temperature part and the part which is still pressurized. So the vacuum is used to temporarily to isolate in terms of temperature the instrument from the environment, but the actual spectrograph itself is pressurized, and the pressure is also controlled to 10 to the minus 4 precision. So basically what they're getting is that the instrument is intrinsically stable on the level of few tens of centimeters per second. It's also stable on a time scale of years, which is very important because if you want to look for Jupiter, you have to sit on a planet for nearly 10 years to cover the orbit, in fact more than 10 years. And the main problem is to figure out where the zero point of the instrument is, because the instrument provides you relative stability, but it doesn't provide you absolute stability. And for that, the reference spectrum is taking in parallel with the observations, but in different places. So between the spectra of the star, you can also stamp in the references, which is usually thorium argon.
Usually called what?
Which is usually lamp of thorium and argon,
yes.
mixture of these two elements. Thorium provides you lots of lines, and that's an example of thorium spectrum. Here, and argon is the filling gas, which is mostly noise, but you cannot live without some filling gas into the lamp. So basically, the solution in this case is done in the following way. Your cross-correlate spectra taken different dates. Okay, so you just calculate the cross-correlation function, and that gives you the radial velocity offset. So that's the spectrum taken one day, that's the spectrum taken phase phi, and then you calculate the cross-correlation function, and that gives you the radial velocity. Now, interestingly enough, it turns out that the zero-point stability is a major problem. On the way you make a solution, wavelength solution for this whole thing, is actually causing more problem than anything else. There was, in the last 3 or 4 months, there was almost an anecdotal story that where I was involved, and that is people in Geneva were looking for very systematical effects with the data and with the reference, with the thorium spectrum. And once several of those systematical effects were removed, the solution improved to the level which they believe was definitely beyond 1 meter per second, so much better than 1 meter per second. And the way we were looking at those systematical effects were the following. We took one spectrum, or a series of spectra, for one object. Okay, so it was one object. Spectra which were covering a time span of about 6 years or so. And we were trying to take subsets of thorium-argon lines and then use them as a zero-point reference and see if we can how well they coincide. What we discovered was really interesting. That once, as I said, most of the systematical effects were gone, the radial velocity of this object behaved like this, and then back, and then like this. This is a time span of 3 years. And this is about 50 centimeters per second. This was strange.
Yes.
And I thought, how a star can behave like this? But the thing became even stranger when we looked at another object and we discovered the same behavior with the same time span, 3 years. And then 2 weeks ago I was in Geneva, and finally we get somebody for technical stuff to attend the meeting. They said, I know what it is. We change thorium-argon lamp every 3 years. So at this level, we start seeing really bizarre things, which is kind of good if we can discover what it is, and perhaps we can find a remedy for that. What is happening in this case is that partial pressure of thorium and argon changes in the lamp, and thorium lines are shifted due to pressure. So if the pressure changes through the lifetime of the lamp, it shifts the lines rather than moving the stars. So, my personal belief is that people working on that and working very hard will definitely reach the level of few centimeters per second within coming 3-4 years, maybe sooner even. But there are interesting other systematic effects that have to be taken into account, which I will demonstrate in the next plot. But just think about it. The first claim that the hot Jupiters are the dominating kind of planets that we see in the extrasolar planetary systems, of course, were part or strongly affected by the selection effects, and that is, it's much easier to discover shorter period planets. For two reasons. First, the effects on radial velocity is larger, and second, you don't have to sit on the system for too long to discover it. I mean, if the period is a few days, if you sit on the object for a couple of weeks, you're already done. What is less obvious is that it is easier to discover high eccentricity planets. And that's another claim that lots of planets in extrasolar planetary systems are running with high eccentricity, or the majority of them. This is also a selection effect to some extent, because high eccentricity planet, at least in part of the orbit, produce large effect on radial velocities. When they're close to the central star, the effect on radial velocity for the star is large. So if you're lucky enough to hit this part of the orbit, you'll find it. If your planet is on a circular orbit, the effect is more or less the same all the time, and you have to really stay on this for a long time and accumulate with high precision signal over the years to discover it. And also, the third thing is at 1 meter per second, we start seeing lots of intrinsic variabilities in velocity fields of your target, of your star, which has nothing to do or not directly related to a planet, which of course one man's noise is the other man's signal. So lots of this data is actually really interesting for people doing astroseismology and studying stellar activities and so on. Well, star cycles. Just think about people sitting on those data for more than a decade, 15 years. The CAT data set goes back something like 17 years. So one can start thinking of, and the only thing they get from each spectrum that they take is radio velocity, one number. The rest is more or less just sitting there on the shelves, waiting to be explored and discovered. One can think of looking at solar kind of cycles, for example, because the time span is sufficient. So here's the plot I promised. This is all the planets with well-known, where the orbital parameters are known to precision better than, say, 20%, including eccentricity and mass and so on. The darker points are the planets, single planets in the system. Lighter color correspond to planets in multiple planet systems. What is interesting is that if one look at the time trend, where new planets being discovered now are coming on this diagram. So this is orbital period in logarithm in years. So this is 1 year. And this is orbital eccentricity. So what is populated now is this part and this part of the diagram. So that's where most of the newly discovered planets are coming to. And these are exactly the demonstration of the selection effect I just pointed out. It takes longer time to discover planets with small eccentricity, and it takes longer time to discover planets with longer periods. So this part of the diagram is getting more and more populated, and that's the expectation that the eventual look of this diagram will become very heavy here and stretch some distance in terms of period.
This is the size, I guess.
It's the
So
mass.
where would Jupiter be roughly on this?
Jupiter would be here. Oops. No, that was the right direction. Yeah. Transits. Just a few words about transits, and then I'll go through characterization. So, everybody knows what transit is. What if the line of sight is very close to the plane of the orbit, there is a reasonable probability that the planet will actually cross the disk of the host star. And as crossing the disk of the host star will cover part of the disk, and the radiation registered, the overall integrated radiation flux from the star will decrease, and that's an example how you sort of dive in here. This is a fraction. This is a phase, a fraction of the orbital period. There are several huge projects, very active, very intensive, working on exactly discovering planets in this way. I should mention OGLE and TRESS, transatlantic search projects. So these are ground-based, and there are several space-based projects. Hubble has been actively used. I was involved with one of them, but also dedicated satellites like Corot and maybe Kepler will fly, so that we can get that. Here is the Kepler NASA image, how it's going to look like, and it's going to try to discover this kind of events. Why it's so interesting? Well, number of reasons. First of all, if you get this kind of event registered and can combine it with radial velocity, then you discover a number of things. First of all, you get the mass of a planet correctly. Second, you get the size of the planet, and together they will give you an estimate of the density. So these are the most important things that you can work with. How this is done in practice, and that's the work I was involved with. This is a Hubble sweeps field survey. This is also a small internal anecdote. Hubble had out of 3 remaining gyroscopes, 2 started to fail, and NASA decided to shut the observations down and wait until they decide what to do with the gyroscopes. And gyroscopes are the things that tell the Hubble where it's oriented in space and keep it there, and that place. But meanwhile, it was just pointing in one direction. This direction happened to be towards the center of our galaxy, which has lots of stars of different kinds, because it's in the plane of the galaxy, so lots of stars. And we're sitting there for 8 days before NASA decided what to do with these gyroscopes. So we sent in director discretionary time proposal and used the advanced camera for survey to take images in the same region where Hubble was pointing for 8 days every 3 minutes. And that's one of the images from our sweeps survey. It was, of course, officially immediately described as a big, important, dedicated project looking for extrasolar planets. But it was only possible because Hubble couldn't move. It was just staring in the same part of the universe. So this is one of the images. Circles that you can barely see here mark the transits that we discovered. And in this case, the baseline was only 8 days, so these are and we only selected the objects which showed 2 such transits in 8 days. So the longest period we could possibly detect was something like 8 days. That's what it was. So the problems with the transits, as I said, are very informative. They provide you lots of useful information about the planets. They also have problems like what radio velocities do. You need radio velocities to actually verify that what is happening is not some kind of binary star. Combination of triple star on the same line of sight. You can have a binary star and a third star, which will sort of add some extra light and decrease the level of the dip. So you will think it's a planet transited another star, but actually, without radio velocity, you cannot verify this completely. And also, there is a selection effect. Of course, the probability to have transit is higher for short periods. So because in a short period, the planet is closer to the star, so the chances that it will cross the disk are higher. So there is a selection effect of that. Characterization. I will talk about 4 things here. Observations of planet-forming regions, transit spectrophometry, reflected light colorimetry, and direct imaging. So now, what kind of physics, what kind of information, observational information can we derive from the discovered planets observation? So first, the environment where planets are formed, and these are the best images one can get from the formation region of the planets. And this is sort of shadows of protoplanetary disks, where central star can be removed to better or lesser extent. But what you see here is not the disk itself. You don't really see much radiation coming from the disk. What you see is the shadow. So the disk covers the white background behind it, so you see this dark thing. So that doesn't provide you with much information. But hopefully, in the nearest future, one can improve this thing by going into infrared, where disks are much brighter. Transit spectrophometry. I think that was the most successful work so far, although it's also kind of still shaky at this level, but that shows you the possibilities. This is a work by David Champanot from Harvard and his group. Basically, what you can do, if you have a transit, then you also have a situation where a planet disappears behind the star. So there is no radiation coming from the planet at all. It's covered by the star. Okay? So what you can do, you can take spectral region where the contrast between the planet and the star is not very large. So infrared, and in this case we're looking between 8 and 14 microns. And in this spectral region, you compare the images taken where you see planet and the star and where you only see the star. So it's a differential photometry in that respect, which can be done to very high precision. And the points here are those relatively wide bands where this photometry has been done. Is a function of wavelengths. So these are two different obscuration events of the planet, which have been used, and you see that they are quite reproducible, those events. The solid line that goes through it is actually a model, and you see that the agreement is poor.
So the model has large error bars, yeah? No, the model was gray or black.
The model is the line,
black, yes.
The drawn line, and these are the observations. I'm also a little bit skeptical about error bars because of some of the points sort of flying really high. Yeah. But we're getting there. So the point is we are gonna get spectrum. And the resolution and the signal to noise of the spectrum will increase. And of course, the first spectrum will come in the infrared, that's clear, because the contrast is better. But this is one of the techniques that is coming. And in this case, what we are looking at is the actual spectrum emitted, so it's a thermal spectrum of the planet. And planet in this case is a Jupiter-sized monster. In fact, one can even go further and take time series where you look at different orientation as the planet rotates and try to map the brightness or the spectral distribution on the planet as a function of longitude on the planet, although we don't know how fast it is rotating. But this was the first attempt. This is actual derivation, and they claim to have a spot which is warmer than the rest of the planet, and from that, because of the phasing, they derived that in this case, Jupiter-sized planet is synchronized, so it's looking at the same side of the planet, always looks at the star. It's tidally synchronized. Reflected light, that's kind of fun, because that can be done in the optical near-infrared, where all the interesting lines are, for example, ozone and water and methane and lots of other useful things that you can look at. So if we're looking from our perspective where we're looking at, and we have orbit which is somewhat tilted, this is of course the Earth in this case, but assume that's an extrasolar planet, what you will see is that the maximum reflected line occurs in the opposition, and in the quadratures you have half of the planet which is illuminated that you see from your perspective, and that's where you get your reflected light. Now, if you think of spectrum, then if you reference the spectrum to the rest frame of the star here, this spectrum will be shifted plus by as much around the orbit, by as much as for the Earth, 30 kilometers per second, which is much wider than the width of spectral lines. Okay? Because this way it's coming towards you, it's blue shifted, this way it's coming away from you, it's red shifted, and that's for the Earth orbit it's about 30 kilometers per second, the amplitude. The problem is the contrast. The contrast in the optical near infrared is about 1 million, So it's just, you will take a telescope of diameter of several hundred meters to collect enough photons to resolve this contrast. But
So the other was far infrared, yeah? When you said earlier that the contrast was actually
in the
not so
infrared,
big.
the contrast can be as low as a few hundred.
Yes.
Yeah. So, but there are several problems there. Both technical problems and also our knowledge of spectral range and molecular and atomic data is not so good. But in the optical, what we can think is just by nature of geometry, where we have highest Doppler shift, we also have the light which is nearly 100% polarized. Because only photons which are scattered by 90 degrees will reach the observer. We are so far away. It's just the geometry that selects photons which are nearly 100% polarized linearly. So basically, in these phases, all the light we see will be linearly polarized. Because photons which are polarized at different orientation will fly, below, above, or sideways, and will never reach our telescope. So that's kind of interesting. And if you look in polarized light, so you basically put your polarization axis this way and that way and compare the differences, you suddenly improve the contrast by a factor of 1,000 or several thousand. And here is the recent measurements. So this is a linear polarization signal. This is orbit as it looks on the sky. You can position the orbit exactly on the sky, and you see that the maximum polarization signal is achieved in the quadratures. This is work by Svetlana Berdugina at ETH, done with French-Canadian telescope on Hawaii.
But this argument about 100% linear polarization, is that based on some simplification of the frequently scattering process? Or?
The assumption is that most of the photons experience one scattering and then left the atmosphere, which is true for Jupiter, for example. Most of the light that we see from Jupiter, reflected light that we see from Jupiter, is experiencing single scattering.
But you assume an atmosphere?
Yes. Yeah, no, we are talking about Jupiters. No,
Yeah.
we are not talking yet about Earth. Because there we have clouds and water and whatever. Direct imaging, nothing happened really in terms of direct imaging of actual planets yet. So there are a couple of interesting developments. There are several space projects, of course, and most of them are based on interferometers. So you have multiple mirrors that you're flying around, flying information, and you're trying to sort of adjust the separation and the formation of those telescopes in such a way that you will have destructive interference in the center of the field where you're going to put your star, and constructive interference in the parts in the field where you expect the planet to be. Now, how it's going to work in practice is unclear, and there is only one practical experiment flying information, and that is a cluster satellite group for satellites, which can be controlled where the distance can be controlled to precision of meters. Now, here one needs to control the distance to precision of a fraction of a wavelength, which is somewhat more difficult.
Mm-hmm.
But there is also an interesting attempt to go alternative ways, and coronagraphs is one possibility. So here is an example of a coronagraph, which is using exactly this polarization principle, where the contrast between the central point where the light is suppressed and the area, which corresponds to about 10 astronomical units around it, the contrast here is 10 to the 7th, and that has been demonstrated in the lab. So if that will really work on a big telescope, this was a small telescope in the lab, then that will beat the 1 million contrast that we need to detect.
Is this in the visible or near?
This is in the near infrared. Yes. Actually, 1 micron. It works at 1 micron already, so it's not very far. Okay, model requirements. The last part, just last few minutes. I will talk about planet formation. I will talk about irradiated planetary atmospheres and polarization scattering in planetary atmospheres. So, planet formation. I would predict that within the next 5 years, observations will probably see disk gaps, density waves, magnetic fields, turbulent velocity field, and chemical stratification as function of radius around maybe 20 stars. Yeah, with planets, it's perhaps even more than a single planet. So we're talking about young stars that still have disks around them where planets are still forming. We're not talking about all stars with formed planetary systems here. Interpretation of the data we will not see planets in those systems because of the disk, partially, and because the imaging is still far away, I think. But we would really need a realistic 3D models of the disks as a whole to interpret the data properly, to convert the spectra and the line widths and velocity field measurements into physical conditions in the disk and try to actually convincingly demonstrate that those disks are forming planets and how planets are formed. So I think that's a challenge for modeling, and that has to be done soon because, as I said, it's coming definitely within 5 years, so maybe sooner than maybe I'm too pessimistic. So here is a simulation how the second generation instrument on the VLT interferometer, an instrument called Matisse, is going to see the disk. Is going to see a disk with embedded proto-Jupiter. So it's a planetary core that has a mass of about 10 masses of the Earth yet to become Jupiter eventually. So this will probably be the image that we're going to see, but we will also see the velocity structure, radial velocity structure, and we'll also see at least some information about chemical stratification in subspace. As for the planets, observation will definitely provide low resolution spectra in the near and far infrared, either created by planets or scattered from the central star. And to get physical conditions, we need model atmospheres for the planets. Because if we're going to get spectra of the planets, to convert those spectra to the physical conditions, what is the atmosphere? What are the temperature, pressure, what is the vertical structure of the atmosphere, the extension, and chemical composition, that will require essentially model atmospheres, similar to what we do with stars. And of course, there are all sorts of complications compared to stars. You get dust, and you get clouds. You get if it's a rocky planet, then you have seasons. You have underlying water or land, and all sorts of climate issues. But the most important thing, which we have to take into account, is the fact that the planet is irradiated. And that's the first attempt on such first principle model atmosphere for a planet done by Peter Hauschel, where irradiation shows the thermal contrast, and there is a night and day side to the atmosphere.
So what was this curve?
This was the temperature. It's logarithm temperature here.
On the surface, yeah?
Yes, so this is the atmosphere.
Yes.
It's a rocky planet. And you have irradiation that's coming from the bottom.
Yes,
this is the evening sun.
Yes. Mm-hmm. And that was in the atmosphere of the planet?
Yes.
And how thick was the atmosphere? It was rather thin, right? I mean,
yes.
Like less than 5%.
I think in this case, the model, if I'm not mistaken, the model was it was a 5 Earth mass planet with relatively thin atmosphere on a rather short orbit. The orbit was 1 month the year, and so that's the model he came up with. Apparently, this planet cannot sustain thicker atmosphere and will not evaporate. It will be unstable. The last thing is my sort of nearest prediction. I would think that the first real planetary spectrum with signal to noise larger than 10, probably 20 or so, will be obtained in polarized light, and that's coming within 3 years. That's my prediction. The spectral range will be between 1 and 2.5 microns, because that's the range we understand well, and that's the range that contains lots of interesting spectral light. But because it's a polarized spectrum, and the physical conditions, the properties of the atmosphere or the outer layers of a planet where the spectrum will be obtained, or maybe several planets, are unclear. So what do we do with it? We really have to look if anybody understands how polarization works. And actually, for the Earth atmosphere, people understand rather well how the forward scattering works in the atmosphere, blue sky, and so on. But the scattering that sends photons backwards or sideways, and the level of polarization in this case, not to mention polarization in the atmospheres of planets like Jupiter, is not very well known, really, because there was no need for that. So these are the challenges for theoretical work, I think, plenty of them. In my conclusions, we need advanced global models for protoplanetary disks with prediction for the radiation, emerging radiation, both high-resolution spectra and overall spectral energy distribution. And we need planetary atmosphere models. Questions to be answered, and of course there are many, but the immediate interesting questions will be origin of turbulence in the disk, because we need turbulence, as you know, to form planets. Chemical stratification as a function of time in the disks, and the history of the particle growth from small dust particles all the way to planetary cores. Thank you.
Thank you. Thanks, Niklas, for a very interesting talk. Question, please.
Coming back to this, your last prediction here about signal, this one. I mean, this recent methane observation, the signal to noise was probably less than 20, and it wasn't polarized, I guess. So
it was. Also, you can see from the far infrared spectra that David Charbonneau was taking with this transit or obscuration technique. We talk about signal to noise in flat. This is, you can squeeze lots of models within this segment. At 20 will be already, you will see features relatively.
So what is the main difference between now and 2011 that will make this possible?
There are 3 instruments on the way. There is a copy of the HARP spectrograph that is built by Harvard, and that is going to Palma to be installed in the 4-meter British telescope. This will have polarization capability that HARPs still don't have. We are building a polarization extension or option for HARPs, which should be operational next year for the original HARPs of ESA. This is a contract between Uppsala and ESA. And there is a low resolution polarimeter, which is called Sphere, which is going on one of the VLT 8-meter telescope. That is 2010.
Okay. The iodine spectra you showed for the calibration in the beginning, it looked a bit noisy.
No, there is no noise. It's just that's the resolution of the screen.
Okay.
It's all lines. in fact, it would be nearly perfect for there.
Yeah.
So it's the thickness of the line, but
Aha, okay.
these are all spectral lines. There is no noise here,
Okay.
really. And I can show you, stretch it, and so on. There are 400,000 lines between 8,000 angstrom and 7,000 angstrom.
But you said they heated it to 100 Celsius. I mean, iodine is gas phase at room temperature, so why do they want to heat it?
I think it's the boundary condition. They want to get rid of the effects of the walls, and somehow when you heat it up, walls become irrelevant. It sort of maintains thermal equilibrium in the center apart when they shine through the center.
In the present state, could we, if we by miracle have a 1 centimeter per second precision observation, could we get rid of the 1 meter per second uncertainty due to stellar activity, or is it something which really needs to be dig into, or what's the current state on this aspect?
Basically, the consensus currently, and that has to be still verified, is the following. Most of the solar-type stars have periods of oscillations of various acoustic waves propagating through their outer atmosphere, which have much shorter timescales, so shorter periods. So basically what you have to do, you have to sit on those objects for a long time, and then the internal motions in the atmosphere will average out. They will come out as a noise. So that has been demonstrated, at least for Jupiter planets, that's really the case. Jupiter-sized planets. If you sit on a planet for 5-7 years, then you can get rid of it to high precision. But we're still talking about 1 meter per second. Now, below 1 meter per second, that has to be demonstrated still. There is no instrument that can.
So it's still a barrier right now, 1 meter per second in this respect.
1 meter per second is the level where measurements are reliable. Below, it's not very well tested yet. But considering the size of the groups working on that, and considering the amount of money being pumped into it, they will come up with some ingenious ideas, I'm sure. Not to mention the fact that, as I said, astroseismology community gets a free ride in this respect. Spectacular material to analyze for oscillation frequencies.
And just 15 years ago, I mean, even the oscillations were rather weak compared, of course, to the convection velocities. The convection velocities can be a kilometer per second, right?
Absolutely, yes.
So we are talking about a signal which is 5 orders of magnitude below the convection velocities.
Yes, but this is kind of fun because convection velocities averaged over a disk of a stellar disk. They come up with line shifts and asymmetries, and those are relatively stable.
Mm-hmm. I see. So can you actually use the line asymmetry, the bisector, even to help you disentangle the two?
Oh yeah. This is absolutely done. Yes, and even people are looking at various indicators or proxies for stellar activities, like flares and changes in the overall level of stellar activities to actually sort out a spectra that corresponds to different activity stage of your object.
When you said you wanted to determine and monitor and verify particle growth, can that really be done with optical data, or should one eventually go to infrared?
No, I think the trade-off between optical data and infrared is the following. In the optical, purely instrumental, we have all the parts that are extremely well understood. We have the best detectors. Infrared detectors are 2 orders of magnitude worse in the noise parameters and the level of signal to noise you can get. we also very well understand the spectrum in the optical. So going too far infrared becomes much more problematic. People didn't have much use to detail spectral information in those spectral regions before. But of course, the gain is the contrast. And there is one more point that I have to make. The angular resolution goes as lambda over d. So if you go to the infrared, you lose angular resolution. So that is another important issue. But in the infrared, you gain the contrast. So the contrast is as the detectors in the infrared will improve, and people will learn more about spectral information in infrared. I think yes, particle growth. I would guess information will primarily come from the infrared.
And how much do we know about planetary atmospheres? I mean, I imagine we are completely in our infancy here with this topic, because, I mean, it's like 100 years back in time when people started to do stellar atmospheres, and that was probably so much.
No, it's not that bad.
Planetary atmospheres.
It's not that bad, because people did work on the atmospheres in the solar system. The difference between stellar atmospheres and the planetary atmospheres is very similar to the situation in terms of or planetary dynamics 20 years or 50 years ago, where people were basically working on the theories that will describe one point, the solar system. And that worked fine. So everybody were happy. People with in celestial mechanics meetings, I don't remember where it was, but I like the presenter who was walking next to the board and saying, we together with Leonard Euler did this. So he took people like from several hundred years ago as his co-author, because the overall thing sounded so stable and so finalized, and no news would come up. So you can have co-authors with a time span of several hundred years. And then suddenly things changed. Suddenly migration came about. Planets are not formed as they end up in the planetary system. Planets are affecting disks. Disks are affecting planets, and planets are affecting each other. It's all dynamic. It's all. It was quite an explosion in the overall dynamics of planetary system. I think we are going through the same phase with planetary atmospheres, where people were basically fitting the models in such a way that they will reproduce the Earth atmosphere perfectly. The seasonal variation, daily variation, and things like that. And they did some work on Jupiter, and did some work on Mars. Did less work on Venus, because that's more complicated, and there is all this greenhouse effect, runaway greenhouse effect. But then suddenly now we have all sorts of situation where we have Jupiter-sized planets, which has a period of 2 months or so very close to the central star. Tidal effects, there is differential rotation, all sorts of things, evaporation, you name it. So it will take quite some work to straighten this out and then produce a coherent picture of planetary atmospheres.
Coming back to this Geneva technique of stabilizing the spectrometer, it seems a little bit primitive method to me to have a high pressure chromium lamp where you have not only pressure broadening but pressure shifts that are. I mean, I would have naively thought that you have a highly stabilized laser or something to do this.
There is a problem with the laser, and laser. Yeah, well, okay. The problem with the single mode laser is that it produces one reference.
Yeah.
That's bad, because what you want to do, you have this shell spectrum, so you have spectral orders sorted out in this way, and the whole thing can break. If we're talking 1 meter per second and better, the whole thing can shrink and change and distort in different ways. So you want reference that will homogeneously cover the whole thing. Thorium produces in between 3,000 angstrom and 1.2 micron, some 100,000 lines, which are more or less homogeneously distributed. There is an annoyance from argon that is stronger, that has much fewer lines, but these are bloody strong, so that's kind of annoyance. So that's why thorium is used. And of course, they thought that because it's a closed bomb and it has a fixed lifetime, they never go 5 years with the same one. They know it's 3 years that will last. But the effects of pressure are very important. And the idea was that if you control the current, you control the temperature, and you control the pressure. What people did not realize that the partial pressure between thorium and argon changed in time. This was, it didn't work at 1 meter per second. It's a 50 centimeter per second effect. It's still an important effect nowadays. What people are seriously working on as an alternative reference is a laser comb, where you have frequency doubling, and then hopefully in frequency you'll have equispaced lines overall. That will be much better. But it's still, unfortunately, you can do it in radio. In millimeter wavelengths, that's not a problem. But if you go into the optical, the lines in those laser combs become so close that they start overlapping, and resolving them is not a trivial thing. But people are working on it.
Right. Good. So if there are no further questions, then thank you again. And at least I'm getting hungry pretty soon, so if some of us want to join us for an early lunch, then you can just stay here.